The winter cold arrives without warning. Outside, the wind cuts across barren hills where temperatures plunge to minus 30 degrees Celsius. Inside a massive turf structure stretching 30 meters across the Icelandic landscape, a family sleeps on raised wooden platforms. Livestock breathe heavily in the darkness at the far end. A single fire glows in the center, yet the building holds warmth that defies the brutal arithmetic of survival. 54 kilograms of birchwood burned daily should vanish into the frozen air within hours. Instead, the interior remains stable at 12 degrees Celsius, cold by modern standards, but far above the lethal freeze outside. This is the Viking longhouse, and it functions not as a shelter warmed by fire, but as a thermal machine engineered to trap, recycle, and generate heat from sources most civilizations never considered. The question is, how did the Vikings achieve this and survive that extreme cold? The longhouse emerged during the Viking Age, roughly 800 to 1050 CE, a period historians call the medieval climate anomaly. Temperatures across Scandinavia ran 1 to 2 degrees warmer than in the centuries before or after. The Norse expanded into Greenland, farmed marginal land, and raised cattle in regions that would later become uninhabitable. But the relative warmth was deceptive. Cold snaps still drove temperatures to minus 30, and the longhouse was designed not for average conditions, but for the worst nights of winter. The nights when exposed livestock died and food stores froze solid. When the climate shifted centuries later and the Little Ice Age began, even a drop of 1 or 2 degrees broke the system. The Greenland settlements collapsed. The thermal machine had been running at maximum capacity all along. The longhouse adapted to its environment with brutal efficiency. In mainland Scandinavia, where oak forests thrived, builders raised timber frames and filled walls with wattle and daub. In Iceland and Greenland, where trees were nearly absent, the same culture built entirely different structures. They cut blocks of peat, called hnaus, and strips of grass sod called stranger, stacking them into walls over a meter thick that tapered inward toward the roof. The structure was partially sunk into the earth, built against hillsides to exploit the ground's natural insulation. The roof consisted of 3 layers: an inner layer of peat with grass facing down, compacted soil in the middle, and an outer layer of peat with grass facing up. Twigs were placed beneath the sod to protect wooden rafters from rot. The result was a building with enormous thermal mass. Dense, heavy materials that absorbed heat slowly and released it even more slowly, stabilizing the interior temperature against the violent swings outside. But this was not a step backward in technology, as you may think. Turf and earth outperform timber in one critical dimension: they prevent heat from leaving. In regions where fuel was scarce and forests vanished after initial settlement, reducing heat loss mattered far more than generating additional warmth. If you cannot sustain the fuel supply, you must make heat loss nearly impossible. Inside, the structure followed a 3-aisled plan. 2 rows of wooden columns ran the length of the building, supporting the massive roof. The floor was packed earth, often spread with ash to absorb moisture. Along the walls between the columns, raised wooden platforms extended the length of the interior. These platforms stood 0.5 meter to 1.5 meters above the floor, and this elevation was not decorative. Cold air, being denser, settled at ground level. The platforms lifted inhabitants into a warmer layer of air, creating a microclimate within the larger structure. Experimental archaeology conducted in reconstructed longhouses confirmed that temperature differences between the floor and platform levels were significant enough to determine survival. The longhouse had no windows. Openings in the walls would hemorrhage heat, so the Norse sealed the envelope almost completely. Light and ventilation came from controlled vents near the roof ridge called vindauga, which is translated as wind-eye and is the origin of the English word window. These were not transparent panes, but deliberate gaps that allowed smoke to escape while minimizing cold air infiltration. Hot gases from the central fire rose immediately to the ceiling, accumulating in a layer near the roof. Below that smoky zone, the air remained cooler but breathable. The smoke escaped through the vindauga, and fresh air entered at lower levels. But the system kept the warmest air in the inhabited zone.
The fire itself was the Langgelder, the long fire, positioned in the central corridor. It provided light, heat, and a cooking surface where iron and soapstone vessels hung above the flames. But the fire's fuel demands were staggering. Studies of reconstructed longhouses in Iceland found that even during summer, daily household needs required over 54 kilograms of birchwood. Projecting that demand across a harsh winter revealed the unsustainable scale of reliance on combustion alone. Deforestation followed Norse expansion across the North Atlantic. The central hearth could not be the primary heat source. Used for cooking and emergency warmth, in Greenland, farmers sometimes had to carry weakened animals out to pasture in spring because the creatures were too frail to walk after months indoors. But the animals provided something beyond their agricultural value. They were living furnaces. A single cow generates substantial metabolic heat simply by existing. Multiply that output by a small herd, contain it within a heavily insulated envelope, and the effect becomes measurable. Even when external conditions plunged far below zero, this heat was constant, required no labor beyond feeding, and depended on no scarce resource. The Fehus transformed a biological necessity into a thermal asset, demonstrating a principle that circumpolar cultures worldwide discovered independently. Shared body heat is infrastructure. However, the trade-offs were severe. Smoke from the open hearth accumulated in the upper air, and inhabitants lived in a perpetual haze. Archaeological studies of skeletal remains show chronic respiratory damage, sinusitis, scarred lung tissue. Darkness was constant, and the interior was lit only by firelight. The air constantly smelled of livestock, smoke, and damp earth. 12 degrees Celsius is not warm. It is only merely above freezing level. Modern humans, accustomed to heated homes, would find the conditions intolerable. But intolerance was irrelevant, because the longhouse was not designed for comfort. It was designed to prevent death. The structure also carried spiritual weight. The fire of the Langgeldur is connected to Norse cosmology, where the universe emerged from the collision of primordial fire and ice. The domestic hearth represented imposed order against chaos, a controlled flame holding back the frozen void. Flanking the chieftain's high seat were the Onvegisúlur, carved pillars inscribed with divine symbols that channeled ancestral protection. Early settlers in Iceland threw these pillars overboard when sighting land, claiming the farm where they washed ashore, a ritual binding family fate to place. The house was both functional and consecrated. Actually, the longhouse succeeded because it integrated 4 systems: passive insulation through turf and earth, biological heating from livestock, active fire management through stratification, and personal insulation from wool and fur. Remove any single element and the system failed. The margin for error was non-existent. When the Little Ice Age began and temperatures dropped even slightly, the thermal machine broke, and Greenland's Norse vanished. But for centuries, the Longhouse worked. It transformed earth, animals, and fire into a survival engine that modern reconstructions confirm was more thermally effective than anticipated.